Okay, let's take a look at technological applications of radiation. I'm going to skip the warm-up and scroll down. There are a lot of different applications of radioisotopes, and we're going to talk about how they are used in devices in your home and in medicine and research and recreation. So if we take a look in your home, for microwave ovens, we use the microwave oven to heat up and cook food. And cooking occurs when the microwaves actually cause the water and fat molecules in food to vibrate more rapidly. And that generates heat, and the food cooks internally and typically faster than if it were in the oven. If the food is thick, that means the microwaves may penetrate it unevenly, which is going to cause uneven cooking. And another problem with microwave cooking is the air temperature that's inside the oven. It's room temperature, so you don't get a crust forming on your food. So you may have noticed that some microwave food actually comes with a cardboard or a foil sleeve, and the air inside that sleeve gets really hot, and it has the ability to cook the outside of the food, which is how you get your crust to form. Now, smoke detectors use a small amount of americium-241 to detect smoke in homes and other buildings. This isotope is going to emit alpha particles, and they ensure the flow of electrical current through the detector. And when smoke enters the chamber that contains this isotope, it interrupts the current, and that's when you get your alarm. Now, americium-241 actually emits gamma rays in really small amounts, but the benefits of being protected from a potential fire far outweigh those radiation risks. Let's talk about medicine on the next page. A more advanced version of an X-ray is computer axial tomography, or a CAT scan. And a CAT scan passes X-rays through the body, and those rays are picked up by detectors, and there's a loop around the person or the object that's being scanned, and the X-ray source moves around the loop, and then you get this picture. And the detail in a CAT scan is a lot greater than an ordinary X-ray. Sometimes bone shadows can obstruct some of the view. In cancer therapy, most commonly this is known as radiotherapy, and we can use radiation to weaken or destroy diseased cells. And some cancer cells are really sensitive to radiation damage, so if we can target the cancer cells that are in the body, radiation can be used to destroy those diseased cells while minimizing the damage to your healthy cells. There are a couple of common methods for delivering radiation. One of them is irradiation, and the second one is an implant. Now, irradiation is when we take a radioisotope and let's use cobalt-60 as the example that they've given, and a beam of cobalt-60 gamma rays. Now, the rays are focused on the tumor, the cancer tumor, and then over a course of treatments, the goal is to destroy the cancer cells. And if we're using implants, implants are more of a small radiation source that perform the same function as cobalt-60, but they put them inside the body. Now, nuclear medicine has radioisotopes that are also used for different medical tests. A lot of times they're going to inject a radioisotope into a person. For instance, technetium-90 is used to obtain images of the brain, thyroid, lungs, liver, spleen, and kidney. Sodium-24 studies electrolytes in the body. Indium-111 studies the brain and infections and colon transits. In science, carbon dating is an example of a scientific use for radioactivity, where we can figure out how old something is by the percent of carbon-14 present. In industry, they can use something called structural flaw detection. This is where you have gamma ray photographs that have the ability to show flaws in welded joints or metal casings. And radioisotopes can also be used to find leaks in underground pipelines. If you add a radioisotope, which they call a tracer, to fluid in pipelines, you can use a Geiger counter to detect the buildup of the tracer. And that buildup happens wherever there is a leak in the pipe. Now on the next page, they've given us some other industrial uses for radioisotopes. Chlorine-36 measures sources of chlorine in the age of water. Gold-198 traces factory waste. And zinc-65 helps to predict the behavior of heavy metals in mining wastewater. Now let's talk about recreation. Tanning beds. Tanning beds use ultraviolet lights to give you a tan, but it's a little more complicated than that. There are two types of UV rays. There's UVA and UVB. UVB rays are sometimes called burning rays because they cause burns on your skin, but UVA rays can actually penetrate deeper and they can cause damage to your cells, and that means they can also damage collagen and elastin. So that means UVA rays can cause wrinkles. Tanning beds tend to use lights that produce more UVA than UVB rays. So the chances of skin burns are reduced, but there's a greater chance of you getting deeper tissue damage. So if you want to protect against skin damage, you can use sunscreen, which is going to prevent UV rays from penetrating your skin. Now let's talk about the effects of radiation on living organisms. All forms of radiation can be classified into two categories: either natural or artificial radiation. I wish I could make this smaller. There we go. That looks better. Okay, now, this figure summarizes the sources of radiation that a human could possibly be exposed to during a lifetime. For natural sources of radiation, that would be 82%. Non-natural would be 18%. And you'll notice that radon would be the largest natural source of radiation, and this occurs naturally as a gas and comes from the alpha decay of uranium that's present in the Earth's crust. Radon is not really a problem because it doesn't react easily with other substances, but it is easily breathed in and out and has a half-life of about 4 days, and the problem arises when this attaches itself to dust and you breathe in those radioactive particles, and then they could become lodged in your lung tissue and then pose different health problems in the future. If you're outdoors, the concentration of radon is pretty small, but if you're indoors where airflow is minimal, then you run the risk of having larger concentrations of radon. So you can monitor radon levels in your home by purchasing a detector at a hardware store. Let's take a look at the next section: human exposure to ionizing radiation. So radiation with enough energy to remove electrons from atoms to form ions is known as ionizing radiation, and it can damage cells. And there are 4 types of ionizing radiation that you may be exposed to: alpha particles, beta particles, gamma rays, and X-rays. The Earth's crust and cosmic rays from space contribute to human exposure to ionizing radiation. If we're talking about the damage that's done to humans by ionizing radiation, we measure it with a unit called the rem. And an average yearly dose of radiation from natural resources is about 0.3 to 300, 0.3 rems or 300 millirems. And that dose comes from radon or cosmic rays or rocks and soil or something that you consumed. Artificial sources of radiation come from medical and dental x-rays or nuclear medicine or consumer products. So the normal yearly dose of radiation for an average person in North America is going to be about 359 millirems. Let's talk about the effects of exposure to ionizing radiation. So there are small amounts of ionizing radiation, like the amount a person naturally receives each year, and they don't normally cause health problems. But if a cell is destroyed by exposure to ionizing radiation, typically the body can make a new cell, And there are some exceptions, like neurons and female sex cells, where damage can't be repaired. But exposure to larger doses of radiation in a short period of time can also cause a lot of damage to the body because it damages your cellular DNA, which can lead to the death of a cell. If you have one cell dying, that's not that serious, but if you have a lot of cells dying at once, then the whole organism could die. And if the cells don't die and continue to live and reproduce in their mutated state, then the actions of that altered cell could eventually lead to a disease like cancer. Now, there are too many X-rays without proper protection could potentially damage your cells. That's why you get covered with a lead blanket before you get a dental or medical X-ray. X-rays are really valuable medical tools, so the information that they provide tends to outweigh the possible damage to your cells. There are a couple of different types of radiation that cause damage to living things. This is somatic and genetic. Somatic damage applies to any part of the body but the reproductive organs and can lead to cancer. So if you get a high dose of radiation and get ill with radiation sickness, like you get nausea, fatigue, you lose your body hair, or you can die, that would be an example. The other one is genetic damage, which applies to damage of your reproductive cells. And this is commonly called a mutation and is generally harmful to future offspring. Now, let's talk about using radioactive technologies. So, technology that uses radioactivity is, yes, a risk, but we balance it with the benefit that the technology can bring. So, for instance, nuclear power plants and radioactive waste storage facilities. You probably don't remember, but in 1986, you probably weren't around, there was a nuclear accident at Chernobyl in Ukraine. There was an explosion and a fire that caused radioisotopes to spread over parts of Europe, and it was 100 times more radiation that was released than that from the atomic bombs that dropped on Japan during World War II. Some would argue that this accident is a reason for banning nuclear power generation. Other people argue that long term, the total number of deaths from that accident was a quarter of the deaths caused by automobile accidents in the United States in a year. But one accident definitely doesn't tell the whole story. And there are a lot of factors that you have to consider when assessing the risks of nuclear power generation. Those risks would include things like, are there risks to workers working at the plant or people that live nearby? And is there risk for a failure, some sort of catastrophic failure of the plant? And are there risks associated with disposing the nuclear waste? Now, when we're talking about disposing nuclear waste, that comes from nuclear reactors or hospitals and industry that is going to remain radioactive for thousands of years, you have to safely store it somewhere. So where would you store something like this? What do you store it in? And how do you mark the site so that other generations know that it's extremely hazardous waste? So in the United States, there's a proposal to store solid radioactive waste in caves found in Nevada. And this is a stable geological area, and it could hold the material with little disturbance from events like an earthquake. But a potential problem is having water leak into the containers, and then it mixes with its contents, and then maybe it ends up contaminating the groundwater. So the risk assessment that has to occur before you actually store nuclear waste is going to take a lot of research and different meetings and discussions.